Okay, everyone can hear me? I'm on? Great. All right, so this talk today that I'm about to give, it's really designed for 3 different types of people. The first is the person who's writing our code today. They're going against relational database servers, and they're kind of just running into a lot of performance issues, and they're struggling. That's use case 1. The second kind of person this talk is really designed for is the person that is using Hadoop today, and they're running their pig jobs, their Hive queries, but they really kind of miss those, that functionality that R and these other packages gave them. And then the third person that this talk is for is just for that person, who's using Spark today and just wants to kind of know where R fits in that ecosystem. And so with that, I'm going to talk a little bit about who I am and where I came from. So I'm a healthcare and life science solutions architect. What that means is I help our partners who are in the healthcare and life science space either build or move their applications onto the AWS platform. I got my start in biostatistics many years ago. I was working at the National Cancer Institute, and I was kind of building these cloud architectures before we even had that buzzword of cloud. At that time, it was just distributed systems programming. But when I was working there, I got pretty interested in what these biostatisticians were actually doing. So I ended up going back to school, got an MPH in biostats. And so with that combination of computer science and statistics, I ended up being the manager of the data science team at Memorial Sloan Kettering Cancer Center, which is this major cancer institute in New York City. But for now, I'm here at Amazon. And this is just to highlight some of the partners that I work with. You'll see there's a lot of household names up there like J&J, but at the same time a lot of new innovative startups like DNA Nexus who are really changing the way that we look at genomics data. So at this point in the room, everyone's kind of thinking, all right, healthcare guy, what are you doing here? Big data talk, get to what you want to talk about. And so this is why I'm here. It's guys like President Obama, and he's pushing for things like precision medicine. And if you're not familiar with that term, precision medicine, it's an emerging approach for disease prevention and treatment, and it takes into account a particular person's individual genes, outcomes, lifestyle, and environment. And really, Obama puts it best when he says, doctors, they've always recognized that every patient's unique. Doctors have always tried to tailor their treatments as best they can to individuals. And you can match like a blood transfusion to a blood type. That was an important discovery. But what if matching cancer cure to genetic code was just as easy, just as standard? What if figuring out the right dose of medicine was as simple as taking our temperature? And that's really the goal of precision medicine. But to do that, we really have to collect a lot of data. Because it's not just all the genomic data that's in our bodies, all the different variations, but then even your outcome data, things like what's on your cell phone, how does that relate to all these gene variants, how do you do those complex queries? So for a long time, bioinformaticists have had these HPC clusters that they could spin up, and they would have a clustered computing algorithm to analyze the genes of one person. But now that we're talking about doing these population studies across huge populations or even countries, you really have to think outside of what you can do in a HPC cluster that just sits in one data center. It's really about how do we take advantage of cloud computing. And so, there's been various attempts to move into the Hadoop world because a lot of these, genomic algorithms, they do get parallelized pretty easily, so you can run MapReduce on them. But for the most part, the bioinformatics community, they've shied away from going into Hadoop. And that's not for a lack of trying. There's been projects like BioPig, but really just the sequential nature of Hadoop and just kind of the interactivity and the type of languages that the bioinformatics and statisticians wanted, it just wasn't quite there until more recently with Spark. And so if you're not familiar with Spark, I'll talk a little bit more about that in a second. But basically, it was a way that you could start having these big scalable queries in the language that you were most familiar with working with. So, R is a relatively newcomer. Python's been around for a while. Spark is actually written in Scala. But starting in Spark 1.4, R actually got integrated into the Apache Spark distribution itself. It's now a first-class citizen with the rest of the languages. And starting in the newest version of Spark 1.6, they've actually done a really good job of all of the documentation. So if you wanted to learn Spark with R as your entry language, you can do that pretty easily now. And so one of the other things that the statisticians and the analysis really loved is that Spark was fast. And that's a relative term, obviously, when you're talking about petabytes of data. Fast could mean different things to different people. But the takeaway that this slide is really trying to get at is it's massively parallel, but still does a lot of those things that your RDBMS used to do that you know and love. So for instance, it uses DAGs. So you can kind of think about that in terms of how your relational database had an optimizer. It minimizes I/O by storing RDDs in memory. In other words, unlike Hadoop, Spark actually knows how to pull data into the memory that's sitting on these clusters, so it's not just wasted. You also minimize it's smart enough to minimize a lot of the I/O. Sending data across the network is a slow process. Spark is smart enough to kind of put the data where it belongs, so you can minimize some of that. And then the last bullet point goes with the other one, which is you'll avoid a lot of those network intensive shuffles, and that helps it be quote unquote fast. And so where does Amazon come in here? So this is kind of one of the reasons I came over to work at Amazon and came to the cloud, because when I was a statistician, I was not a huge fan of doing this IT setup. AWS made this really easy to do myself though, because even though Spark, it's not that bad to install yourself, there's just a ton of configurations and different settings that you really have to factor in. And the EMR team, they have a great understanding of all of our underlying infrastructure for AWS, and they've optimized and configured all the Spark settings to do really pretty much what you want it to do or expect it to do. Now, you do have root access to these instances, so if you did need to make a change, you could do that. But for the most part, for the rest of the talk today, we're just going to go on the assumption that the EMR team nailed it, and we can just go forward. Oh, sorry, back to this slide. So yeah, it's easy to install and configure. You can quickly add and remove capacity, so you can take advantage of all of the cloud native tools that you're thinking. It's easy to, it comes with a Zeppelin UI. With a checkbox. If you don't know what that means, it's a nice GUI interface that's in a web browser. Think you're like an IPython notebook for Spark specifically. Now that does not yet work with R, but it's easy enough to install R Studio, which I'll show you in a minute. You get different pricing variations, so you could reserve your cluster for the whole year with reserve pricing, or you could take advantage of something called spot instances, which is our way of getting rid of unused compute capacity. So Amazon, if we have unused computers, no one's using them, no one's paying for on-demand, you can actually get those at a very cheap rate, and that's all integrated into Amazon EMR. It also has a lot of security features that, again, the EMR team came in and did a great job. Me being in the healthcare space, I have to deal a lot with HIPAA and a lot of compliance regulations. And if you start looking into how a lot of these big data technologies work under the hood, and you have to worry about, all right, where is this data getting spilled to? Where is this sensitive data going across the network? It gets very tricky very fast. But the EMR team's made a lot of great progress. It's made my job a lot easier for meeting a lot of compliance regulations. And then finally, with Amazon EMR, another advantage is you can really decouple your compute and your storage. And that one is worth going into on another slide, because that's going to take a little bit of explanation. But what that really means is that you can have all of your data sitting in Amazon S3. It's hot storage, but you're paying for very cheap compute. Now, behind the scenes, you're only paying for the data once. Behind the scenes, it is replicated 3 times. It's secure. It's 11 nines of durability. But for the most part, you don't have to worry about that. You put your data in S3, and it's safe. But then you can start spinning up your Spark clusters or other types of clusters, optimized for different things, and go out and get that data, petabytes of data, whatever you need to do, and start cutting it up. Different analysts can come in and look at that same source of data, and you don't have to keep pulling the data around or moving the data around. And then it's as easy as with doing your Spark context.txt file, and you can create an RDD with that. So if that made sense to anybody that's actually using Spark, that's all it takes. So let's look at that in the context of how it would work if you're doing a SparkR analysis. So there's probably 3 different types of clusters you could have. So you might start with a bunch of transient clusters that might be running spot instances that are just generalized compute. they're going to come in, take your raw log file, take your raw data, whatever it happens to be, and then do a bunch of aggregations, a lot of data cleanup. And then you can put that data back into S3, and then take those clusters down. At the same time, you might have a long-running cluster that's optimized, very memory-heavy compute, so you can have a lot of different analysts coming in and doing their descriptive statistics there, doing their, setting up their models, and they're going against a nice GUI like Zeppelin or R Studio. And then finally, once they've got those models ready to go, and they want to put those out in, and actually run across petabytes of data or terabytes of data or whatever it is, you can spin up yet another compute type, so you're not going to be competing with your analyst, and it can be optimized for, compute-heavy workloads. It'll spin up, and then it can go away as soon as that job's complete. And the way all this works is it all writes back to S3 and reads from S3, so you have one source of truth the whole way. And so let's see what it actually takes to get that cluster up and running. So this is pretty much all it is you're going to come into the console. I clicked on my EMR. I'm going to go to Advanced Settings. And these are all the different applications I can install that will be managed and installed for me and configured correctly. I took away Pig, but I installed Spark. Here's where I'm going to add a step where I could be a Spark streaming application. And this is what I was describing with the transient clusters, where I might just come in, put in one job, and then have this automatically go away. I can click that auto terminate and just have it go away as soon as that job's complete. At the next step, here's where I'm adding how many pieces of underlying nodes I'd like. And there's 3 different types. A master, who controls everything, the core, who can actually store data, and then the task, who are just extra compute. And that's a good place that you can integrate with the spot market because it's not storing data. So if it gets taken away from the cluster, it's just taking away extra compute capacity. But if you have it, it'll give you more compute capacity, and you get your job done faster for cheaper. You can also, all the logging is integrated with Amazon S3, so by default you get nice durable logs you can save off to. And then finally there's something called a bootstrap action, and what this lets you do is you can have custom code that runs as soon as your cluster comes up. In this example here, I'm going to put in a R Studio bootstrap action that's going to install an R Studio GUI onto my master node. And what I'm doing here is I'm just picking basically a bash file from Amazon S3, and I will walk through what that file is actually doing as soon as this is over. And then here I'm picking a security group, or a key that I can log into my master node with. Security groups, if you're familiar with these are layer 4 firewalls that surround your instance. Talk to one of the solution architects here if you want more info on that. And at that point, we're just waiting for this thing to start. So this is usually the hardest part, is the waiting. So if you can't hear it, Todd Petty's letting us know that we're waiting. And it's the hardest part. And you just got to have faith that it's going to work out.
It's not faith. It works out.
But almost always it's going to work out. OK, and now we're waiting. So what waiting means is I got a job, and I'm about to start, and I'm just waiting for a job. Give me a job. Let's go. And if I want to do this again, I don't have to do all this. I can go to that AWS CLI export, and I can put that into a command line. I can put that into a cron job, whatever I want to have that whole thing run again. What I'm doing now is I want to get into that master node. So I'm going to get my, this is all in the GUI, so you can just kind of copy, paste, and go. And I'm going to put the SSH command to get into my master node. I'm sorry, this is not getting into the master node. What I'm doing is port forwarding, so I can start my local websites that are running there. Once I do that, I've highlighted in the console. This is Zeppelin. This is pretty much, if you're writing in Spark, probably your go-to. But, and I just wanted to quickly show how you would get into Zeppelin. But what I'm going to do here is I'm going to change the port. And I'm going to go on the R Studio port. And then there's my copy of R Studio. And as part of that bootstrap script, I also dropped on how to connect to Spark context. If I was running in the Spark shell, I wouldn't have to have this line. But I need a way that Spark can talk to the Spark context. And if that doesn't make sense, that's OK, because I'm going to talk about what that actually means here in a second. But basically, I'm running SparkR now on a cluster. And that's all it took, a few minutes, and we were up and running. So what did that actually do? So R is all pretty much local. All your R Studio stuff, that works as it used to work. And all SparkR really is it's a library, it's a package. And then there's a connection point, that R JVM bridge that talks to our typical Java Spark context. That's the exact same context that you're going to use no matter what language you pick in Spark. So the magic of SparkR really here, it's all in that R JVM bridge, because that's what's taking you from R, translating to that Java context, and then everything from there works just like it does in any other Spark language. It's just the same RDD API. And then on each of the workers, you get a local copy of R that knows how to talk to the executor, but you're relying on Spark to actually distribute all the data and all of the execution patterns. And if you're an end user, like I just showed you in that console, you never have to worry about any of this, but I thought it was cool, so I threw it in here. And then what that bootstrap action did is R Studio, there wasn't a nice checkbox for like there was for Zeppelin, but it's pretty easy to install yourself on the master node or run that bootstrap script to do this automatically. This is the code. We can share the slides so you don't have to worry about writing this down. A little tip is R Studio, the users there, they rely on whatever your Linux users are. So if you don't really do this in production if you have sensitive data, but my little workaround is I just go in and add my analyst users to the sudo file so they can do what they want. I don't have to worry about permission issues. And then at that point, you do have to, like I said, this is the part where I was talking about, you actually have to connect your R Studio back to this Spark context. You have to tell it where to go. This is the command to do that. If you're already familiar with Spark, this might look a little bit familiar to you. But basically, same way you would initialize other Spark settings, you're just going to say, hey, where's my master node? In this case, I'm saying it's local star, which means run across my local machine on every core that you can get a hold of. So in this scenario here, this would be the same setup that you would normally have if you just ran this on your local desktop. If you want to run this across the Spark cluster, how your SparkR console shell would work, you're going to want to point this at yarn. And then there's instructions to, actually a great reference for all this stuff is on Tuesday, a blog post went out that actually has all these instructions as well, and they can walk you through this. That's on the AWS Big Data blog. All right, so now that's all the nitty gritty. I'm up and running. I have my Spark cluster. All right, what can you actually do with SparkR? Oh, so what happens when you have an RDD, which is your R data set with R? You get R2D2, and that's actually not my joke. That's Shervan's joke. Here's from the AMP lab right up the street here. He was a big help for getting a lot of these resources out here. He's one of the writers, so I just wanted to give him a quick thanks. And he's also the one who came up, showed everyone that architecture pattern as well. So what does the SparkR API actually give us? So it gives us a few things. We get our I/O, and again, that's I/O that we can go get right off of Amazon S3. It gives us caching. Now, a lot of people new to Spark that I hear, kind of a misconception, is that everything in Spark is in memory, and that's why it works so well, it's so fast. Not exactly true. It can use memory, but you have to actually call that cache on your data set to actually put it into memory and let it know, hey, put this into memory. Then there's some utility functions, things that you're probably used to working with in R, things that will let you filter, get your counts. And a big one that's really popular is that that generalized linear regression model. And that lets you do big scale predictions. Lots and lots of log data, and now this is a great way to actually scale that, that regression analysis that you're trying to do. Now, it's relying on the MLlib package, and if you're familiar with MLlib in Spark, there's a lot more here than just a regression model. It's not quite in SparkR yet. It's on the roadmap, but that shouldn't make you scared to get into SparkR because of this thing called a register temp table. What this will do, and this works the same across all of Spark, is you can start out with Spark with R, and you can do your big aggregations. You're familiar with R, so you just want to start cutting up your data, your big data sets, get what you need. And then when you're ready to actually run a model, you could do a register temp table, And then that will let you pick it up in the same, as long as you're in the same context, Spark SQL context, in the same Spark application, you can pick it up and then in a different language and then start running the functionality of a different language, which is a very cool feature of Spark, that you can go back and forth between languages. So pick the right language for the right job, and then have all the data still sitting in S3 or all in Spark. Now this register temp tables, just so you know, that's not persisted. So as soon as that application dies, so does that table. But there is a way you can do a save as table, and that will take advantage of the Hive metastore and save what you have in the Hive metastore, so that table will still be there, regardless of when you come back to the cluster. There's a lot more on that in the Spark programming guide.
So, in addition to this, is there any work being done to integrate SparkR with kind of these flyer tools that currently exist? Okay.
So, great lead-in. Yes, so SparkR is a dplyr-like syntax, and so they are trying to make it look a lot like dpylar. And so yeah, so if you're familiar with that, you're going to pick up SparkR and just kind of go. And so that's the main part of SparkR today, is this DataFrames API. And it's going to read in things, your regular things, but then also things off of S3. And the performance is going to be comparable to all the other Spark languages. And the reason why, it's because, again, you're going through that same RDD API that you would for any other language. So very, very simplistic example of what you would look like. You're going to start with your URL to anything that's sitting in S3. That star could be thousands of files. I've done this across like all of the, it's called a TCGA data set. It's a big genomics data set, and it works. And then you're going to read in as a text file into this lines. So I'm just basically counting lines here. And then I'm going to convert that to a data frame. So this is an RDD. I'm going to convert that RDD into a SparkR DataFrame. And then that lets me start doing my aggregations, my counts, and my filters as I would in R. But across, this could be massive amounts of data, as opposed to what could fit in your memory on your laptop or whatever you're working with. Or even if it's an HPC cluster, your HPC cluster at one data center that's static. And then finally, the trick here, what I'm showing here is this collect. What collect is doing is it's dumping all the data out of that SparkR data frame, and then it's putting it into a local R data frame. So for that functionality that's not there, so I showed you how GLM was there, but for things that are not there yet, you can still dump, do your big filters against that Spark data frame, that big data set, and then get it to a reasonable size data set that you could then do your analysis against. But I know that's a little unexciting because, okay, you showed me how to take big data, get it into small enough data, and so there is work being done to get more into SparkR. There's a new, there's an entire new API that will be out in Spark 2.0 as that gets released. That's going to solve a lot of these problems. But in the interim, there is a workaround because that exposes the underlying RDD that you can take advantage of. Now this is going to go away. So I know a lot of the Amazon EMR guys are sitting right now shaking their head being like, why are you telling people to write this code that's going to break? And it's because a lot of times for data analysis, you just want an answer to your question once, and then you can kind of move on. And this is a good workaround to deal with until that functionality really comes along. So what this is the RDD, it gets exposed as an R distributed list. And so that means you can run all of those R functions that you're familiar with for a distributed list against these RDDs. So your list applies, would let you go across that RDD and run whatever function you want. So this is a great way you can have a function. And then what you do is you just include this package into that Spark context. That means it's going to load that function across that entire cluster, whatever you have. It's smart enough to do that. And then you can actually run this RDD, this function across every line of that RDD. And so that's how you can actually scale R today, any function that you'd like. Even though that's going to go away, that is still there underneath the hood now in Spark 1.5 and 1.6. So use with caution, but I find it pretty useful. And then finally, I'm going to leave today just by just showing you very quickly how to run a very simple GLM on SparkR. In this case, I'm not going to go through our studio, but rather in the console. I've logged into the master node, and I just typed SparkR, which is now spinning up my SparkR shell. So I'm in my SparkR shell, and I'm going to create a data frame out of the Iris data set. If you're not familiar with this, this is coming straight from the SparkR tutorials. Iris data set is a pretty famous data set for machine learning where you have a bunch of different types of flowers, and you're trying to predict what that species of flower is going to be based on some data about it, such as like how long are the petals and that kind of thing. So what you're seeing here is this is what the data set actually looks like. I have these different petal lengths, and so now I've just run my regression model across this. And I can take a look at what my regression model came back with. There's my beta value estimates for how likely something is going to happen. My p-values look really good. And so now I can basically use this to create predictions on new flower species that I'm seeing. In this case, I'm cheating it because I'm basing it off the training data, but you can get the idea of what's happening here. And now I'm going to quit the console. And I'm sure that was less thrilling to most of you that have done this regression models before. But the key takeaway here is now I'm going to go back into, I'm going to open up those ports to get back into the console again, and so I can start looking at those web applications. And I'm going to go back into my EMR cluster. And I'm going to take a look at what that job actually did. And you can see what's actually happened here is I'm going to open up this event timeline, is I actually spun up multiple executors for a regression model. And that is kind of the magic of SparkR, is that you can have these regression models and then have all underneath the hood without you having to deal with anything other than, here's my typical R code. Now all of a sudden scale my data set across whatever nodes or clusters that you'd like. And an on-demand nature where you can take it down when you're done. And so with that, I just wanted to thank everybody, the big data team, for having me. And up next, if you have questions afterwards, I'll be around. And I do have to catch a flight, but Andrew here from the EMR team also is a great resource. So with that, I'm going to hand over to Corey, who's